Day 141, a lesson on resistance. You should have already done some reading about how resistance varies with the type of material, the length of the wire, the temperature of the wire, and the width of the wire. When you put all of those ideas together, you get this equation right here. I put the R over 1. You don't have to have that 1 there, but it helps to see things a little bit. The R is the resistance, and that will be measured in ohms. Then we have this P value, and sometimes that's called rho for the Greek letter, that's P. And that is a number that's grading the wire's material according to how well it can conduct electricity. And you're always going to be given those numbers over here. The capital L here is the length of the wire, and that has to be in meters. On the bottom we have pi and r squared. That is the radius of the wire. Don't forget to square it. It's easy to forget. Now, all of our tools that measure things like the radius or the width of a wire will not give us the radius directly, but rather give us the diameter. So remember that in your story problems, you have to cut the diameter in half to get the radius, and then you put that number in. Okay, so from this equation, it's important for you guys to understand inverse and direct relationships. So let's repeat it, even though we've done it before in other kinds of equations previously this year. Both the R and the L are on the top in the numerator. And so therefore, if I double the L, I'm going to double the R. That's called a direct relationship. If I cut the L to be a third, the resistance gets to be cut to be a third. In our reading, we found out that the wider the wire, the less resistance. But it's not a simple relationship like that because we have this squared here. So a little change in the R is going to result in a big change in this capital R. If I cut the radius to be half, the resistance is going to quadruple. If I divide the radius by 3, I'm going to multiply the resistance by 9. This power of 2 is the thing that messes things up. Okay, so a small change in the R results in a much bigger change in the resistance. This little r, remember, is the radius. Okay, so let's do the first problem here. Number 1, what is the resistance of a 3.9 meter long germanium wire with a diameter of 6.4 times 10 to the negative third? Now, first of all, let's look at this 6.4 times 10 to the negative third. 6.4 times 10 to the negative third. That negative 3 there means that we move the decimal point over 3 places, 1, 2, 3, and then fill in the missing places. So that is equal to the diameter. If I want to get the radius, half of the diameter is going to be this. Now notice if I put this into scientific notation, it is still times 10 to the negative third. I only cut the front numbers in half. The power of 3 doesn't change. Okay, so there's my R value. I need to find the P value. Sometimes you'll hear me call that the rho value. Okay, this is known as resistivity. And we have that in our little graph or table up here. The resistivity of germanium is 0.45. The length of this wire is given to us as 3.9. So now we have enough information to substitute into our equation. R is equal to PL all over pi r squared. The P is 0.45. The L is 3.9 meters. Then we have our pi and 0.0032, and we got to square that. Okay, now there's lots of ways of typing this in, and many of them are wrong, so be careful. I have the 0.45, and I'm multiplying that times the 3.9. That's on top, so they're multiplied together. The pi is on the bottom, so I'm going to divide by pi. I can get an equals there. And now the top is also divided by this term here. So I'm going to hit divide by again, 0.0032, and that's squared, so I hit the squared button. And now the equals, and I get my answer of 54554 point something something something. So 54,554 ohms. Now I can do this another way, this mathematics. I can just multiply the top, 0.45 times 3.9, and get an answer, 1.755. And then I can multiply the two things on the bottom, pi times 0.0032 squared equals, and I get 0.00003217. Now, dividing the top, 1.755, divided by 0.00003217 equals, guess what? The very same thing, 54,553. So that's one way of doing it. There's a third way. Some of you are going to see this on the bottom, pi times 0.0032 squared, and you're going to insist to multiply pi times that. And that's fine, you can do that. Now here's how you do it. 0.45 on the top times 3.9, and then we're going to divide by parenthesis pi times 0.0032 squared, end parenthesis, and then equals. And I get the exact same 54,554. So there's three different ways of doing it. Choose the way that your brain works best, but be careful with it. Okay, next one. What is the resistance of a 4.3 meter long copper wire with a diameter of 0.0002 meters and a temperature of 20 degrees? Assume all the wires are cylindrical. Okay. This seems like a really small number, but remember, a meter is pretty big, the width of a door, and so we want a very, very small fraction of that for the diameter of a wire. This is actually 0.2 millimeters, which is a legitimate measure for a wire. Okay, what is the resistance? We're looking for the R of a 4.3 meter long copper. Okay, so that 4.3 is going to be for the L. So let's write down R equals, the L changes to a 4.3 meters. Copper wire, so I look up here for copper, and copper is the second line, 1.7 times 10 to the negative 8th. Let's write that bigger. I'm going to multiply that times the, what was it, 4.3? Okay. Has a diameter of 0.0002 meters, so that means that the radius here down at the bottom is going to be 0.0001, and we got to square that, and we got to bring down the pi. Okay, so typing this into my calculator, 1.7 EE negative 8 times 4.3 divided by pi, and I'm also going to divide it by the 0.0001 squared equals 2.3. And the unit for resistance is ohms. Let's do this math in a different way. 1.7 EE negative 8 times 4.3 divide by, I'm going to do parenthesis, pi times 0.0001 squared, end parenthesis, equals, and I get the same 2.3. Okay, next. Number 3, you're trying to figure out how a certain machine was made. An unlabeled wire is 0.099 meters long. It has a diameter of 0.6 times 10 to the negative 6 meters. It has a resistance of 9,900 ohms. What type of metal is in the wire? So, if we look at our equation, it's the p-value here that is distinctive between the options of aluminum, silicon, and germanium. So if we can figure out the p-value and then use this chart here, we can figure out what the material was. Okay, so the R is the resistance, 9,900 ohms. The P is the unknown. The L is 0.099 meters. Then we have our pi, and the diameter is 0.6 times 10 to the negative 6. So the radius is 0.3 times 10 to the negative 6. Remember, you only cut the first number in half. The power here does not change. This is the number of decimal points that you move, and that doesn't change, just change the digits. Okay, next. We want to get the P by itself. So I'm going to multiply both sides. Multiply both sides by pi, 0.3 times 10 to the negative 6. Pi, and also 0.3 times 10 to the negative 6. I'm going to multiply both of those. So, 9,900 times pi times 0.3 EE negative 6 equals, on the right hand side I get 0.0093. 0.0093. I'll throw in another 3 there. That equals P times 0.099. These cancel, those cancel. Okay, so I now need to divide both sides by 0.099. Divide by 0.099 equals, I get 0.0942. Whoops, I forgot to square this. Drat. Okay, we gotta back up here a little bit. Oofta. This should have been squared. So I needed to have that squared and this squared over here. Okay, so we just have to redo that last step. 9,900 times pi times 0.3 EE negative 6 squared equals. Okay, that is 0.123456783. Yep, 8 zeros with a 3 at the end. That equals P times 0.099. And now I divide that by 0.099, and I get 0.1234. 7 zeros. 1, 2, 3, 4, 5, 6, 7 with a 2, 8. That equals P. Okay, now, nowhere in this chart do I have a whole string of zeros with a 2, 8, so I got to change this to be scientific notation. So I'm going to move the decimal point until I get a number between 1 and 10. 1, 2, 3, 4, 5, 6, 7, 8. So 2.8 times 10 to the negative 8th is our p-value. Which thing is that? That's going to be aluminum, the third line. So number 3 is aluminum. Number 4, if you double the cross-sectional area of a wire, what happens to the resistance? Once again, the equation R over 1 equals PL all over pi R squared. So the radius and the resistance are on opposite sides. They are inversely proportional. When one gets bigger, the other one gets smaller. But it's more complicated than that. With that squared here, a little change in the R, a little change in the resistance makes a big change in the, I don't know if I said that right. A little change in the radius makes a big change in the resistance. But the question here is, if you double the cross-sectional area, what happens to the resistance? Just simply, does it increase or decrease? Okay, so doubling the area is going to be making this bigger. So that means the resistance gets smaller. The answer is going to be B, decrease. Number 5, if you cut a wire to be shorter, what happens to the resistance? If you cut a wire to be shorter, the L value is going to get smaller, and the L is on top just like the resistance. So if that gets smaller, the resistance gets smaller. Number 5 is going to be B, decrease as well. Number 6, if you have two wires that are equal in every way except one is longer, which will have more resistance? The longer the wire, the more the resistance. They're both on top. So the longer the wire, the more resistance. Letter B, option B, the longer one, is going to be your answer. Number 7, you make a wire out of iron and its resistance is 34. If a lead wire had the exact same dimensions, approximately what would the resistance be? Okay, so iron, looking up at the chart here, iron has a p-value of 10 times 10 to the negative 8. Lead has a p-value of 22 times 10 to the negative 8. About double the p-value. We can see here that both the resistance and the p-value are on top, so they are directly related to each other. If you double one, the other one's doubled. We basically doubled the p-value from 10 up to 22 times 10 to the negative 8th. So I'm going to about double the resistance. If the resistance of the iron was 34, I double that and I get 68. There we go. Sorry about that with the screen. So I found the p-value of the iron to be 10 times 10 to the negative 8th. And for lead, it was 22 times 10 to the negative 8th, about doubling this. So if I double the p-value between the two wires, I'm going to double the R value, the resistance. So doubling 34, I get 68 ohms. Number 9, everything else being equal, which would have more resistance, a warm wire or a cold wire? From your reading, you should have found out that the higher the temperature, the more the resistance. And so option A will be your answer. Number 10, everything else being equal, what would have more resistance? A wire that's 12 millimeters in diameter or a wire that's 6 in diameter? The wider the wire, the easier it is for electrons to go through. So the 12 millimeter is going to have less resistance. The 6 millimeter is going to have more resistance. So number 10 is the option B is your answer. Number 11, everything else being equal, which would have less resistance? Silicon or copper? Silicon, 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 silicon. Down here, 640 for the p-value. And the copper is a 1.7 times 10 to the negative 8th. Remember, at 10 times negative 8, that means that the real number in plain old digits is 1, 2, 3, 4, 5, 6, 7, 1, 7. A very small number. This is a very big number. And we're putting those in for the p-value here. So the smaller the p, the smaller the resistance. The bigger the p, the bigger the resistance. The question is asking for which has less resistance. So the one with the smaller p-value is going to have smaller resistance. The copper is going to have less resistance.